All right, let's continue with the discussion on vectors, right? So where are we? We talked about what a vector is, magnitude, direction. I gave you an illustration, a real life illustration, so you can appreciate vector and direction, and also kind of hinted to you how we'll move away from just that one dimension where all you care about is a positive or a negative if you want to denote direction left to right, right to left. Yeah, this is now real life, right? Remember I told you I was gonna move, and here's what I'm doing. I have conveniently assumed some distances here, right? So I've got my box, no friction, yeah, don't worry about it. Don't worry about the mass of this box for now, or these boxes. But very simply, the string is used by me over my shoulder to apply a force of F newtons on this box, and this is where I've tied it. What happens, right? And this is where vectors and manipulating these vectors becomes important, and we will get into it through this example. So displacement, I mentioned, as a vector of this box is going to happen in this direction, right? This is the direction of displacement. So this is the vector of displacement. However, the force vector acts in this direction as I'm tugging on this string. I want to know, clearly the movement is this way, so I want to know what's going to transpire here. Any calculations, you know, this thing's momentum changes, its velocity, initial velocity is 0, it picks up some velocity, maybe accelerates a tad bit too, but all of that's going to happen in this direction. I need to translate or rather equate this force into something along this direction, so I can do the momentum, change in momentum calculation with respect to force, try and get something meaningful. All my calculations will need this force to come into this direction. So I am now going to talk about resolving, which is the term, resolving this vector into its component along another vector. And I'm going to give this an angle, okay, of theta. And that will be the variable that will help us resolve this force, this vector, into its component in the direction of the displacement vector. So I will resolve the force vector into the direction of the displacement vector. How are we going to do this? Let's look at the trigonometry part using this, right? So trigonometry would tell us some things, right? I have obviously given you these dimensions just to make it easy for you, but you could use Pythagoras theorem and calculate them. But let's take a look at what theta is. Theta here is, if you look at theta here, I could say that the cosine of theta is 1 meter divided by 2 meters. So I could say the cosine of theta is 1/2. Wow, that makes theta, look at that convenient selection of numbers by me, about 60 degrees, right? Okay. So if I brought this and said, okay, I'm not really physically moving this vector here, but I'm just looking at the effect of this vector along the direction of this vector. Then you would go back to your trigonometry and say, we also know the cosine is the adjacent side divided by the hypotenuse, which means my adjacent side is nothing but the hypotenuse times the cosine of the angle. Now if I use that idea here, the force vector, and this time I'm going to write the force vector here as the green component is an F, and now because this is horizontal, I'm just going to use a little H here, too small for you to see. So here, the horizontal component FH, but watch this, right? I'm getting the vector here is equal to the force vector itself times cosine of 60 degrees cos of theta. We know theta to be 60 degrees, cosine of theta is half. I would actually get this as 1/2 of my force vector. So just half of its magnitude gets into this. As I manipulated the direction, the magnitude changes. So while FH has a directional component, what I've really gotten here is a magnitude. The direction got taken care of here when I added the cosine, and it also took its magnitude out. So by doing this, I'm actually writing just the magnitude, because the direction is already specified when I provided the theta. So I've actually taken direction out, and in reality, what I have is really a scalar value that gives me a magnitude in this direction. This is important. We are resolving, and that's why I wanted to show this to you with an example, right? We're resolving this because we know intuitively if I did drag it, it would move along the ground. Of course, there's other reasons, because this is really heavy, because if it was in space, it would move along the direction of the force I was pulling it, right? There's other reasons for it, but this is resolving a force, or resolving one vector into the direction of the other vector. Obviously, if it had a horizontal resolution, it would also have a vertical resolution, or a vertical component that it could be resolved to 2, and that, you guessed it, would be the sine of the angle, because its opposite is hypotenuse times sine theta. This would be sine theta times this force vector, sine 60 degrees, 0.86, I think, or something like that. So it would give you another value there, right? So that's just an example of resolution of forces. Now, I also posed a problem for you where I said, hey, you're a student of physics, you really know a lot of cool things. You walk past me and you tell me, hey, what are you doing? Why don't you just tie it on your waist, tie the string on your waist, and you should be good to go. And go like, oh, okay, what happens if I did that? And if my waist isn't either high, so if I drew that line here, just take a look at what happens. Assuming I gotta probably use another color. Or maybe we'll stick to white line. Stick to this white line. If I did that, sorry to make it messy, but now suddenly what happened to theta? If this is 1 meter, this is 1 meter, two sides equal, theta is 45 degrees. Suddenly the directional resolution, or the component in this direction, would now be F horizontal is that force vector times cosine of the new angle, this angle, call it theta dash, or would be theta dash. We know from trigonometry, if this is 1 meter and this is 1 meter, theta dash is 45, cosine of 45, 0.7, I think, approximately. So I would actually be doing 0.7 times, whereas in my previous example, and again, this would be a scalar quantity because the direction is already in here. So I've actually just taken the magnitude of the force, or magnitude of the component of the force in the direction of displacement vector. I actually have more because the previous one was 0.5 times force. Now I get a better horizontal component, meaning I can exert more force in the direction that I want motion of, which means this is a lot more efficient. And you can see here how this part of physics and this kind of math comes into benefit in real life, because you actually begin to understand that, hey, if I was going to push a trolley, maybe I should move my elbows this way and push, because I'm applying maximum force in the line, parallel to the direction of motion, versus if I were to do this and push, where I would be sending the force, in a different direction, and only its horizontal component would have an effect in the direction of motion. So I would be much better off. So this is a very simple, tying practical application to understanding the vector, understanding directions in 2 dimensions, and how you want to start thinking about vectors being resolved into components along other vectors, right? That is an important idea. Cosine, therefore, is an important angle to remember. Anytime you see a vector has direction and magnitude, and another vector has direction and magnitude, and they are subtended by an angle theta, you always imagine the cosine to be the factor that brings, maybe, you know what, let's not do this. Whilst my pizza is getting, let's just do that. So it doesn't appear like, a horizontal line. It's that is theta. You always think of taking this vector's magnitude with cosine of theta and then bringing it up here to get the full effect of what happens. And this is typically how you want to remember it, theta and the cosine of theta. So if you had A and if you had B as 2 vectors, you would get another component here, A, maybe I'll call it B prime, would be equal to B cosine of theta, and B prime would be along the same line. So A, and then you might get an addition of B prime along that direction. So hopefully it gives you an idea of what we're trying to establish here, and I'm trying to give you a visual view on this, right? So this is key. So let's keep that in mind, and let's extend this a little more, right? Let's extend this into a world of, well, this is great, looks nice visually, a little bit of trigonometry, fantastic, but how do we manipulate these in a little better manner, right? We want to understand how to play with them, which means we want to give them meaningful directions. Algebraically, we want to give them directions which are very easily, some kind of numerical values, if you will, right? And for that we need coordinate geometry, and therefore we need algebra. So let's take an example. Okay, that's my pizza oven beeping. So I'll be done in 3 minutes, and I'll leave you with this concept again, and you can work this out. So if I have my x-axis here and my y-axis here, think about it this way. If I define, and this is mathematical convention, right? If I define a unit vector, magnitude 1, but as a vector it has direction, along 1 dimension only. So a unit vector. We like to call this I, lowercase I, again convention, yeah? And then I define another unit vector along the y-axis. Hopefully you can appreciate the color. Again, unit vector, magnitude 1, direction, it's a vector, along one axis. This time I'm going to call it J. That's my J. Doesn't look very nice. That's my J. So if I and J are unit vectors along a standard axis, any other vector, displacement vector, velocity, force, however you want to represent it, could be stated as a combination of these two. Okay? So if I had a straight line vector, I could map it out here and just say, oh, here's a vector. And if this was, say, 5, right? 5, 0. Its magnitude, what would the magnitude be? Just 5. That's easy. And by specifying 5, 0, I can now state that, hey, it has a direction. We would now let me restate this. If I set this as 5i plus 0j, it would mean the exact same thing. There's 0 times j, and there's 5 times I. With me so far? Now we'll build on this and say, if I have, let's say, 3, but I also have I could define this point here, 3, 4, and that vector to be 3i plus 4j. What would its magnitude be? Three square, 9, 4 square, 16, sum 25, root 25, 5. That's the magnitude of the vector. But its direction is provided this way. Now suddenly we have a means of algebraically manipulating them. Again, I'll leave you with this thought, but we'll build on it. We won't go too much into vectors at this point. I just wanted to illustrate what vectors are, what kind of notations you'd see, what the geometric view is using trigonometry, how we translate them into coordinate geometry, and then hopefully we'll start seeing how we manipulate them. At this point, most vectors are now being, we're adding on to it. So we did a little cosine component, brought it here. We kind of got a magnitude that acts in this direction. We're not yet talking about multiplying these vectors, right? For now, everything we're doing is really looking at some kind of a component of the vector, an addition of vectors maybe, and we'll get to that. And we'll go into these as we study concepts in physics. So when we study work which is effectively force times displacement, then we begin to say, okay, you got force, you got displacement, you got the vectors coming together. We'll start doing some kind of view on the product of vectors. And likewise, when we do moment, where we have torque and things like that, we'll start doing some other types of vector multiplication, right? But for now, this is the idea I want to leave you with. Understand how vectors are denoted, so you know what they are. When we get into multiplication, we will also see that if you had vectors such as ai plus bj, and then or maybe the better way is a1i and b1j, and you have another vector which is a2i and b2j. These are both individually vectors, so we may call this as a1 vector and this is a2. We might start thinking about what happens when these vectors are, what does it mean to add them? When you add them, in what direction? What does it mean if these vectors, for example, are applying against, if there are forces that apply against the same point, what does that resultant force? And as we do those kind of analyses, then we will see what happens to these vectors and what happens with that cosine angle. But for now, this is where I'll leave you with vectors. Understand this, understand how vectors are denoted and why they are so, because we can manipulate them, we can multiply these in certain ways, we can multiply them in two different ways. We'll probably speak about both of those down the road as we study more about vectors. But for now, I think we should put you in a decent spot in the basics of high school mathematics, and more to come later. And for now, I'm going to have my pizza. See you next time.